Hello, my name is Jacob Parr, Senior Instructor for Databricks. Today we'll be looking at Apache Spark's Cost-Based Optimizer. This segment actually comes from our 3-day workshop, Apache Spark Tuning and Best Practices. To find out more, you can go to databricksacademy.com. Databricks offers training in both forms of self-paced and instructor-led training. All of our trainings are conducted on our own product, Databricks, which is a unified analytics platform that enables data scientists and engineering teams to run all analytics in one place, from ETL to model training and inference at scale. Today we're looking at the Apache Spark Cost-Based Optimizer, one of our techniques for join optimizations. The data that we'll be looking at is synthetic sales transaction. There's 3 tables: transactional data representing the purchases made throughout the course of a year, retailer information such as Walmart, Costco, and other retailers, and then we have location information such as cities based in locally in the US, Washington DC, Chicago, Denver, worldwide, Paris, London, etc. And we'll be joining these 3 tables and taking a look at some of the effects of those joins on Apache Spark. Before we dive into that, it's important to note that Apache Spark was first designed for doing one-shot processing. That is the idea that once we process data, we iterate over it and then we're done with it. So we lack the ability to implement certain optimizations that are typical with relational databases. For example, indexing and other heuristics that allows a traditional relational database to optimize our queries. Some of the optimizers currently available include the Catalyst Optimizer that's responsible for rewriting our code, the Incremental Optimizer, which is used in Apache Spark Structured Streaming, and here today the Cost-Based Optimizer. It was originally introduced in 2016 during a demo at Spark Summit. 1 year later, it was introduced into the product during Spark 2.2. In order to get started here, we're going to start our course with our typical classroom setup. For those unfamiliar with our courses, this is simply initializing usernames, user variables, and other utility methods that we use in the course of our notebook. We have a handful of utility methods for our labs. This would include things such as clearing our results, validating schema, logging our results, and things of that nature. And then a handful of utility methods. Some of these we'll be using in this module, and some of them we will not. We'll start by importing a handful of necessary functions. And the first thing that we're going to do is disable the cost-based optimizer. The reason for this is because within the Databricks platform, the cost-based optimizer is enabled by default, and we want to see what its behavior is like without the cost-based optimizer. We can do this simply by setting the configuration Spark SQL CBO enabled. We can see that it's currently enabled now. We can then go ahead and set that option to false, and we're also going to disable the join reorder optimization. And we'll talk about that a little bit more. As we go through this course, multiple students are using the exact same databases within Apache Spark, and so this is going to create a potential for a name collision. So what we're going to be doing is taking the username variable that was defined above, substringing it to remove the @ symbol, so this is basically an email address, and they're going to create a Spark query that will initialize a database for us. We'll execute that query, see the result of that. And then if we open up the data tab on the left-hand side, we can now see that I have a database called me, my email address being me@jacobparr.com. Next, we're going to define 3 tables in our private database. This will be sales, cities, and stores. We're going to pre-qualify each one of those with the database that we just created. Go ahead and execute those. They declare the variables. In case you're running this multiple times, we're going to go through and delete those databases or drop those tables more specifically. So we'll be dropping table sales, table cities, and table stores. We're going to set the Spark SQL shuffle partitions 8 to match the number of cores for our cluster. That size is also appropriate for the data sets that we're using. We're going to go through and create 3 tables. The first one is the sales transactions from 2017. We're going to read that in as a Parquet file and then write that out as a table. We're going to repeat that process for both the cities and then again for the stores. Go ahead and execute that. Now that the job is completed, we can open up the Data tab and see that within my database, I now have 3 tables: cities, sales, and stores. So from that, we can now execute our first query. So in Spark, we're going to start with our Spark session. We're going to read the sales table, the cities table, and the stores table. We're going to be joining on city ID and retailer ID. In this example, we're going to be using the action for each. It's using an empty lambda expression. It has absolutely no effect on our code, but it does force the processing of our code. Let's go ahead and run that. Now that our job is done, we can take a look at the information. We have job number 79, 3 stages. And what we're going to do is going to go take a look at job number 79 in a Spark UI. So in Databricks, we can do that by selecting our cluster, going to View Spark UI. And we're not interested in job 79 per se. We're more interested in the SQL engine underneath the hood. So we're going to select the SQL tab at the top. And on the right-hand side, we're looking for job 79, which corresponds to query 170. We'll click on the description and look at some more detailed information. From here, we can see we now have our query plan. We're joining 3 tables, me.cells, me.cities, and if we scroll down a little bit, we can see me.stores. The first 2 tables are joined because that's the join order that we specified, joining cells to cities first. As we scroll through this, we can see they go through a shuffle operation, a sort operation, and then a sort merge join. The sort merge join is not the most efficient join operation in Apache Spark, but it is highly scalable, and so it works really well for large data sets. If we take a look here though, we can see that we're outputting a significant number of rows, and then ultimately we're going to come back and do the third join on our stores table. In the case of the stores table, we can actually see that the amount of data that's coming through is roughly 1,000 kilobytes. This is going to allow Spark to do an estimation saying that that join information is less than our 10 megabyte threshold and do an automatic broadcast hash join, which is an efficient join operation. And then it merges the 2 together and produces our final result. Okay, so back to our notebook, we're going to take a look at enabling the cost-based optimizer. So in this case, we're going to go back and set those 2 properties to true. Go ahead and execute those 2 cells. In addition to enabling those options, we actually have to tell the cost-based optimizer to analyze the tables. This is equivalent to a relational database capturing heuristics about mins, maximums, and other information about a table. The analyze table operation, we're going to execute that on all 3 tables, cells, cities, and stores. And with that data optimized, we're going to go back and rerun our exact same query from before. Now that our query is done, we can take a look at the job information. This is job 84. And if we go back to our Spark UI, back to the SQL tab, we can see job 84 corresponding to job 177. Take a look at that. And we'll notice immediately that there's a difference in how our tables are joined. In this case, we have me.cells and me.stores are joined together. As we scroll through there, we can see that this is the broadcast exchange that we saw previously. What Spark has done is it said that the join operation from the large table to the small table would be more efficient. And this is what we referred to in that last time we looked at the diagram, where if we join 2 large tables and then a smaller table, we're going to get an efficient join. Here Spark was able to see that by joining the larger and smaller tables together, we can get a more efficient join. The output of that is going to be a much smaller data set that's going to be shuffled through. And then we're going to go back and join in that 3rd table of cities. In the case of the cities table, it's going to still resort to a sort merge join. It's an inefficient join, but because the left-hand side of the operation is now much smaller a data set, this operation is immediately more efficient. There's a couple of questions that we want to ask here. According to Spark UI, how fast was the Spark off in its estimation of that sort merge join? How much data from the stores table was broadcasted, and why was the cities table not auto-broadcasted? So going back to the Spark UI, we can see in that final sort merge join, zoom in down here, we can see that the final estimation is off by a significant magnitude. And the reason for this is because as we were going through and reducing the data set on the left-hand side, the data on the right-hand side has much less data to join to. But Spark, the Catalyst Optimizer, does not have enough information to do that effectively, so its estimation is off by a significant margin. The other question was, can we get the cities table to be broadcasted in the same way that we broadcasted the stores table? So the stores table is 100 records and very small data set, but the cities table is significantly larger. We're looking at roughly 2.3 million records, and the size of the data coming through is roughly 161 megabytes. At 162 megabytes, the cities table is greater than our 10 megabyte threshold. Because of that, Spark will not induce an auto broadcast hash join. Now, if we go back to our data, and we can say that we have a significant number of records that are being processed, one of the key strategies for optimization is simply to reduce the amount of data that you're processing, or in this case, that we're shuffling. So if we were to come back and say that our cities table is for worldwide cities and we only need to be analyzing cities in the US, we can actually reduce the total data set by eliminating all non-US cities. If we were to reduce all non-US cities, how large would our data be? Let's take a look. One of the strategies for determining the size of our data is simply to cache it. There's a number of problems associated with that, namely to do with the fact that when data is cached in RAM, it's significantly larger than in its natural format stored by the DataFrames API. It can, however, give us a rough idea of how that data is being managed. One technique that we use is a utility method called cache as. We can actually see that in our notebooks by going back and opening up the utility methods notebook. Take a look at cache as. So we can see the implementation of cache as is rather straightforward. Given a data frame, given the name of a table and the storage level that we want to implement, go through and remove that table or uncache it, ignoring any errors that produces. We're going to take that data frame, create or replace a temp view, and we're going to use the name that's specified for the name of the temp view. And then we're going to use Spark catalog that cache table with its appropriate storage level and then return that data frame. Now that we cache the data with cache as, we can go over to the Spark UI, take a look at the storage tab, and see how our data is cached in memory. The benefits of using that temp table means that RDD name is rather concise and short. If you have any experience doing caching on a shared cluster or mini caches, the names can be really convoluted and hard to follow. So this just makes the process a little bit easier to work in the Spark UI. But once it's cached, we can come in here and we can see roughly in memory the size of each partition and the total size of data that we're caching. So in this case, we're roughly 8 megabytes per partition, or total size in memory 64 megabytes. That is nowhere near our 10 megabyte threshold. So again, the size in memory is going to be inflated versus the actual size on disk, but it does give us a good estimation of how large our data is. So the next question is to determine if we can get the data set to be smaller than that 10 megabyte auto join threshold. So what we can do is take that same name that we used in the cache, RDD name. In a Scala API, there's a utility method called get RDD storage info. We can apply a simple filter to our name and then ask for its size in memory. So this is just another technique for identifying our size in memory, 64.4 megabytes, which was the same size that we saw in the Spark UI. We can then do a programmatic evaluation by going to asking Spark for the Spark SQL auto broadcast join threshold, default being 10 megabytes. Go ahead and execute that piece of code. So the question we're trying to answer is the data suitable for broadcasting? We already saw in the Spark UI that it's 64.4 megabytes. We know that's above the 10 megabyte threshold. One of the techniques that's available to us is to go through and programmatically ask what that auto broadcast join threshold is. And so we're going to do a simple comparison of the full size 64 megabytes versus that threshold, the result indicating that it is not suitable for broadcasting because we are about 54 megabytes over that threshold. With that, we have to ask the question is, what is wrong with using the size in RAM to judge the ability to broadcast? So again, the size in RAM is inflated because data stored in the Java heap is significantly expanded as opposed to the data frame's natural storage format, commonly referred to as tungsten binary format, or more properly referred to as an unsafe row. So the next question is, if we reduce this to only the US retailers, can we create the data set small enough to meet that auto join threshold? So going back, grabbing the cache name, Spark table cities, we're going to filter it by state, or filter it specifically where state is not null. So this will give us all the US cities, and we're going to recache that data set, programmatically ask what its size is, evaluate it to see if it's below that threshold, and then print the results. And as we can see, the cache size is 9.6 kilobytes. 10 megabytes is our threshold, so we're well below that threshold, and this should auto broadcast appropriately. So our theory that if we limit to the US cities alone, we should be able to auto broadcast this data. So we're going to go through, rerun our query with one small modification. That is to apply that filter to the state where state is not null. Rerun the query, and then we can take a look in the Spark UI to see how that resulted. With our job completed, we can go take a look at the job results. This is job 88. Again, we'll go back to the Spark UI, back to the SQL tab. We're looking at job 88, query 182 in my case. And if we take a quick glance, we can see that the first join reorder took place, and that was broadcasted, but the second join is still doing a sort merge join. And the reason it failed is here. If we look at the estimation that Cost-Based Optimizer came up with indicates that the actual number of records versus the total number of records is off by a significant magnitude. So based on the Cost-Based Optimizer's estimation, this data is not suitable for broadcasting. However, if we look at the actual data broadcasted, we can see that it was only 4.2 kilobytes of data that was being shuffled. So the question is, why did that not broadcast? Short version is the estimator is off. So we can actually apply a broadcast hint. So as an engineer, I know as a result of that filter operation, it will be small enough, it is suitable for broadcasting. I can programmatically come in and apply a broadcast hint to that filter or to that join so that Spark will broadcast the right-hand side. Go ahead and run that query. And when that's done, we'll evaluate its result in the Spark UI. Okay, now that our job is done, this is job number 91, back in the Spark UI, SQL tab, job number 91, query 183. We can see sales and stores being joined, and that's being broadcasted. And then the cities tables coming in, and that's also being broadcasted. So we effectively accomplished the optimization, but we had to do it manually. And the whole point of the Cost-Based Optimizer is to do this stuff automatically. And just for confirmation, if we rerun that query without the broadcast, we can go back to the Spark UI and see that it is not broadcasting that data. So back to the Spark UI, SQL, our last job being 184. And without the broadcast, we're seeing again, we're back to that sort merge join. So our optimization is only a result of the keyword hint that's applied there. So in order to get the Cost-Based Optimizer to do the optimization for us, it needs more information. It needs to analyze detailed column information. We can do this by executing the query, analyze table, compute statistics, and we're specifically going to compute statistics for city ID and state. This will give us the additional information that the Cost-Based Optimizer needs in order to properly estimate the size of the data after the filter operation. Now that the analyze operation is completed, we can move forward with rerunning our query. So again, that's sales, join to cities, with a filter on the state. So we limit to US cities, and then that third join to the retailer. Go ahead and execute that query. And then back to the Spark UI one more time. So this was job 97. Go back to our queries. Job 97, query 186. And we can see that on the left-hand side we have cells. We have cities. They're being joined and effectively using a broadcast hash join. And then we're joining in stores. It is also doing a broadcast hash join. Notice that the estimation is still off, which is not uncommon, but it's not off by the huge magnitude that it was before. And the Cost-Based Optimizer and a Catalyst Optimizer together were able to determine that after that filter operation, the data set is small enough to be broadcasted and was able to execute our three-way join. In addition to doing the broadcast hash join, just a quick recap, we also have sales and cities, cities being the smaller of two, so we reduce the total data set by joining large table to small tables. That's the effect of the join reorder option. And then lastly, the second larger of the two data sets, which is stores. So one of the questions that we need to ask is what type of user the Cost-Based Optimizer best suited for? It is necessary that the data be relatively static. For example, last month's data. We are having to take that Parquet file, save it as a table, and then perform the analyze operations on it, which can, on larger data sets, be quite expensive. But once that data has been collected, it becomes extremely efficient for downstream users. This would mean that for data analysts and data scientists that are running repetitive queries on this can be very efficient. The act of doing this for a one-time operation, though, for, say, a typical engineer, may not see the payoff. The second question is, when would I use the broadcast hint? As an engineer, the broadcast hint can often be a appropriate solution because we can specifically say when to broadcast the data and we don't have to engage in the overhead of maintaining the cost-based optimizer, especially for operations or jobs that are just going to be executed one time. So this concludes this segment on join optimizations using the cost-based optimizer. As a reminder, this is part of our 3-day course, Apache Spark Tuning and Best Practices. The purpose of this course is to take students through various coding exercises where we introduce them to very common performance problems. In the course of looking at those problems, we teach students how to diagnose those problems and then to go steps further to actually implement solutions for those common problems. If you would like more information on this course or other courses, please feel free to go to databricksacademy.com, and thank you.